Hello, everyone. My name is Francesco Pappalardi. I'm from Rome. I know several people here. I met good friends, people that I'm meeting for the third time in a third country, and I hope also with the other there will be other chances. My topic is finite fields, and I bet more than half of you are already familiar with this topic, but still it's good to tell several things once so that we're trying to get similar level for everyone, at least try it. So I will start talking about fields. And then slowly I will move to a special class of fields that enjoy the property of being finite. Okay, so I'm actually certain that you've seen many fields. So these are examples of fields: the rational numbers, the real numbers, and the complex numbers. So Bas and René already mentioned real and complex numbers, and rationals maybe not, but still this is maybe the first case of a field. And so these are fields, but we also should be careful at the fact that Z, this is not a field. Okay, so fields, not a field. And so I guess I'm ready to give the definition of a field. So F, so I guess F I should add, since a group is a triplet, a field is a quintuple. So we have two operations, plus and times, and then we have, one to the other operation. And so we are making three requirements. The first requirement is that when I consider just the first operation with the first of these two neutral elements, so this is an abelian group. And the second requirement is that when I take this set and I remove the unit that I've just considered, and then take the second operation and the second neutral element, this is also an abelian group. And then these two operations, they should kind of be compatible one to each other. And this is done through an extra requirement, which is the distributive laws. That of course we know what they are. I'm not going to mention. So a field is the set of all this stuff, and I could, thanks to Bas' lecture, I can kind of give it in a synthetic way, but behind it there's several axioms, and so we know that these three sets, they're actually fields, and this is not a field. This is less than a field, because actually the second axiom is not satisfied, because not all elements of Z admit a multiplicative inverse, right? So one of the reasons for which is not a field since, for example, 1/2 is not an integer. I guess this is one of the basic reasons for which is not a field. So these are fields, and this is just a ring. So I'm going to try and use the notion of the word ring as little as possible, but sometimes I might have to. So these are all infinite fields, and that's an infinite ring. And the next ring, I said I was never going to use it, already used it 3 times. But the next ring, 4 times, that I'm going to introduce is the following ring, Z mod NZ, already used by René. And I'm going to introduce it my way, which is kind of, it hides a certain number of formalism here. So to me, this is just a set of numbers between 0. So here n will be an integer bigger than 1. Okay? And so this is a set with n plus 1 elements. And here I'm going to define 2 operations. One which is plus with a sub n here. So this sub is the first time I'm going to put it, and the last as well. And then there's a 0 and 1. So here you go. I have a quintuple. And so if I have I and j in Z mod nz, so I define a sum. And this is just the regular sum if their sum is smaller than n, or it's their sum minus n otherwise. So their sum is bigger or equal than n. Okay? And then I'm going to define a product. But before I define the product, I would like to define the following notation. Okay, so notation. So the notation is the notation mod. So if I take any integer z, I'm going to define by a mod n. So this is the remainder of division of a by n. So a mod n, this is an element of z mod nz, right? When I have 2 integers, in this case a and m, and I make the division, then I get a quotient, and I get the remainder. The remainder is always 0, but certainly smaller than the divisor. Okay? So I have this. And so through this notation, I can also define a product here. If I want to do I times j, this is by definition I times j mod n. So I make the product, then I divide by n, and the result is gonna be my product. And so with all this, this turns out to be a ring. And by ring, I always, during my lectures, I mean a commutative ring. And with identity. Okay, so this is a commutative ring. And I guess the question, I know you all know the answer, but you also know the question. So when is this a field, right? This is always what one says next in this type of circumstances. So when is Z mod NZ a field? And the answer is, if and only if n is prime. And in which case, in this case, we denote by FP, because this reminds us that this is a field, actually, Z mod PZ. Okay, so I like FP. Okay, and maybe we should comment why this is true. Well, certainly, it gives me an opportunity to mention an exercise that you may like to do in your spare time, or that you know very well how to comment. So if I have an element A in a ring is a field where not all elements are invertible. So a field less an axiom. Okay. So if I have a ring, then A is called a zero divisor if A times B is 0 for some B in R. Okay? And the exercise is the following. In a field, there are no zero divisors. Absolutely. You're right. Thank you, Buzz. Okay? So, exercise, show that. Sorry, I have to wait. Show that. In a field, there are no zero divisors. Okay, so one of the consequences of this exercise is the following, that if you have Z mod n1 times with n1 and 2 bigger than 1, okay, this is not a field. And there are two, or better, one zero divisor right in the front of our eyes here. And what is a zero divisor in this ring? N1, right? N1 is a non-zero element. Okay, so I guess also this A, I would like to take it non-zero. Okay, so N1 is a non-zero element here, but times N2, it gives me 0, right? Because I have to take the product, and then I have to make the division by n times N2, and the remainder is 0. So N1 times N2 mod N1 times N2 is 0. Okay, so this is 0, so not a field. Okay, but also FP is a field. So FP is a field. So I'm going to just assume that all axioms are verified. So it's an additive group with respect to plus, and the product is well defined. It's associative, distributive, and everything. So the only thing that I wish to verify here is the fact that every non-zero element has an inverse. So let A be a non-zero element of Fp, And so I have to produce another element B such that when I divide the product by P, the remainder is 1, right? This is what I have to do. Well, in order to produce the inverse, there is a very efficient and actually widely used method, and this is the Euclidean algorithm. And the Euclidean algorithm allows to write the GCD, so this is the greatest common divisor of A and B, as A times alpha plus P times beta. There exist alpha and beta integers. And since P is a prime number, which is something crucial here, this GCD is 1. And also I can play a little bit with this alpha and beta, and I can take alpha in P itself, because either if it's negative or if it's bigger than P, I can kind of perturbate this in order to make it in FP, and then automatically alpha is A to the minus 1 in FP, right? So I'm using the fact that P is a prime at that point, and then I'm using the Bezout, the so-called Bezout identity, right? So this is a field, and for my lectures, this is a very important field. So it's important for our purposes, okay? This one. Now I would like to mention the notion of characteristics of a field. So what is the characteristics? So the characteristic is a number which we associate to the field. And the way we do it is the following. So I consider the multiple of the identity of. So here I let K vary in the natural numbers. So it's 1, twice, thrice, 4 times the identity, and so on. So let's call it this S. Okay, so this is a subset of the field, right? The multiples of the identity. And now 2 things can happen. So it can happen 1, or it can happen 2. So 1 happens if the 0 of the field, this is not in S. I remind you, as far as I am concerned, 0 is not a natural number. It's highly unnatural. So the first possibility is that 0 can be written as the multiple of 1. And the second possibility, the first is that it cannot be written as a multiple of 1. And the second is that it can be written as a multiple of 1. Okay? In the first case, we say that the field has characteristics 0. In the second case, we say that the field has positive characteristics. Okay? In this case, okay, so in this case, what happens is that so exercise Q, the rational numbers, are, in quote, a subfield of F. So I'm going to write it in the following way. So Q, and then here F. But this is not quite right that Q is a subfield of F. But Q is isomorphic to a subfield. So F contains a copy of Q. So if you take the set of rational multiples of the identity, This is a field which is the same field as Q. Okay? But what happens if 0 can be written as a multiple of the identity? Then first of all, we call characteristic of F. This is by definition the minimum K such that K times the identity is 0. Okay? And while in this case, in case 1, the characteristic of F by definition is 0. Okay? In that case, it's going to be a non-zero number. And the remark is that in this case is indeed a prime number. Okay, and why is a prime number? This is very simple to verify. All right. The point is, if I use this, I cannot write immediately, right? Because it has to get dry. So, I don't know. I guess we'll learn how to deal with this. Okay, so suppose that K is the characteristics of a field F, and this is a natural number bigger than 1. Okay? Suppose we have this. Okay? And suppose that K is not a prime number. So K is K1 times K2, with K1 and K2 bigger than 1. Then K is the minimum, right? Is the minimum of a set. So, but K1 times K1 times K2 times the identity of F. This is K1 times the identity of F times K2 times the identity of F, simply because you write down all this K1 times K2 bunch of ones, and then we divide them as we wish, and we get this. And if we get that this is 0, so since there are no zero divisors, it means that either this or this is 0, and this is a contradiction to the minimality, right? So this is a contradiction to the fact that K is the minimum. Okay? So K is a prime. So K is a prime. And another exercise here, which is very similar to this, if not easier, but that's already very easy. If P is the characteristics of a field F, and this is not 0, then Fp is contained in this sense, that inside of F there is a copy of Fp, or a subfield. I haven't said what is a subfield, which is isomorphic. I haven't said it's isomorphic to Fp, but when I say a copy, maybe I think I'll have to push your intuition here. So this is the case when the characteristic is positive. So you see, for a field, there's kind of a very special situation that either Q or Fp, okay, is always contained in any field. In any field. So there's there's kind of two words, right? The characteristic 0 word, when there is the rational numbers, and you discover it immediately because you look at multiples of the identity, and if you never get 0, then there is the rational numbers, or FP, okay? And now we're gonna, for our lectures, we're gonna be more interested in FP, okay? So the next thing, no, please, because, okay. Sorry. Well, yeah, you know better than me. Maybe I will start on this side. Okay, while you finish there, I will do here. Okay. So, the next thing I would like to mention is the notion of polynomials. Over F. So F is always taken for field. Okay. So a polynomial is, if you want to be precise, it's almost always 0 sequence of elements of F. Okay. So this is almost always 0 sequence of elements of F. So this is a polynomial. But in practice, a polynomial F in the variable x is always written in the following form. So a0 plus a1x plus am x power m. And so with this notation, the almost always sequence of elements of F is the sequence a0, a1, am, with the convention that the last one, am, is not 0, because if it was 0, I wouldn't even put it here. Okay, so it's an almost always, and these powers of x here, they just there initially to tell us which element of the sequence I mean. So the coefficients of x power I is going to be the I plus 1 element of this sequence, right? And the set of all polynomials in the variable x is indicated by this notation. And again, I can define two operations in this set. So I can add two polynomials. So it's going to be the set, the sum ai plus, sorry, aj plus bj x power j for j that goes from 1 to m, where f is the sum of aj x power j, and g is the sum. And here j goes from 1 to m. But here it can happen using this notation that I've added a bunch of zeros, right? Because here, not necessarily the two almost zero sequences have the same length. One might have more zeros than the other, but still the sum is defined by this. And the product, so f times g of two polynomials is going to be again a polynomial, the sum for cj x power j. Here j goes from 0 to m plus n. So, well, it goes well, by the way, I've written that here it goes to 2m, except some terms might be 0. So anyways, Cj is by definition the coefficient of the product, the sum for a plus b equals to j of a times bb. Okay, this is an unfortunate notation, but now it's written, so it's too late to change it. Okay, and so f of x is a ring, and so the 0 sequence, the almost always, actually the always 0 sequence of element of f, this is the neutral element with respect to the sum, and so this is going to be 0 in the sense of all zeros, and 1 in the sense of 1, and then all zeros. These are the two neutral elements on the ring of polynomials. And actually, this polynomial ring is never a field. And one of the fastest way to check it is that 1 over x is never a polynomial. Okay? Yes? Yes, I said that this is an unfortunate notation, but since it's so dangerous to delete the blackboard that I said I don't want to change it. Right? You know what I will do? I will just make it this look as an alpha and this look as a beta, right? Okay? All right. And now I'm going to use this part. So this is the ring of polynomials. And here's another small exercise here. Show that no, actually, I changed my mind. I don't want to give you this exercise. So the ring of polynomials seems like an artificial invention, but actually it's very useful in field theory. And I will do this immediately. Sorry, I want to erase my way, that one? No, this is okay. Okay. All right. So next, I'm going to check. So I still have 15 minutes, right? All right. Thank you very much. Okay, next I'm going to make one construction which is really crucial. Okay, so you know what I'm going to do? I'm going to f is a field. No need to specify. F is a polynomial with coefficients in this field. And what I'm going to do, so I have a field. I have the ring of polynomials. I'm going to construct another ring. And I'm going to denote this ring by the following symbol. And I'm going to call this the quotient ring. And here's what it is. So I have to tell you the elements here. So the elements here are going to be so the elements here have this form. A0 plus A1y plus A n minus 1 y to the power of n minus 1. And these are the elements of f of x, f of y. So these are polynomials in another variable y. And, but I stop to the power of n minus 1. Here n is the degree of the polynomial f, which is the maximum non-zero coefficient of f. So I'm taking the respect to the degree to n minus 1. Okay? And so far it seems like I'm not doing anything different from constructing a set of polynomials. And also when I write it, it's not clear what is the dependence on f here, right? But what I'm going to do next on this special set, I'm going to define two operations, a sum operation and a multiplication operation. And with this, I'm going to produce another set of rings. Okay? So when I take two elements, G1 and G2 in this ring, so this ring, I'm going to call it, let's call it R. So if I'm taking two of this, then I want to define, so G of y plus G2 of y. Well, this is nothing else than the sum in f of y. So I'm just going to sum coefficient by coefficient, right? So nothing else. But and still I haven't used f, right? So I sum the coefficient, I sum the polynomial coefficient wise, and then the product, G1 times G2, well, you know, as the product mod f. And what is the product mod f? The product mod f is exactly what you think it is. So if I have two polynomials, g and h, then we can divide them. So in the sense that there exists Q and R, again polynomials, such that two things happen. G is equal, so I guess I can write G as H times Q plus R. So this is the first requirement. And the second requirement is that R is either 0 or the degree of R is strictly smaller than the degree of H. Okay? So I can always do a division, sort of Euclidean division of polynomials. And the way that you can prove that this can be done, and actually quotient and remainder as always 0, is just because you jiggle down with the coefficients and you realize that there's some recursive relations of this quotient and remainder. Okay? And then given this, G mod H, by definition, is the remainder, okay, of the division. Okay? So if we do this, then the product inside this quotient ring is exactly the same. You make the product, then you divide by f, and you take the remainder. Okay? This is going to be our product. And so, fact, this quotient is a, in the sense it's commutative ring with identity. And F is a subring, is always contained in this. So what is the question now? The question is, when is this ring a field, right? This is the question that, of course, we need to make. But before we make this question, I would like to make some one example. So, for example, let's take any field, and let's take as a polynomial the polynomial x. So, what happens here? If I take the quotient ring, so these are all polynomial expressions, polynomial of degree 0, right? 1 minus 1, 0. So this is nothing else than A0, such that A0 is in F. So this is F, right? And this would be the same if I took any degree 1 polynomial, right? The quotient is nothing. The quotient is the field itself. What about if we take field F2 and as polynomial? So let's take a degree 1 polynomial. For example, x squared plus 1. Okay. Then we want to discuss this quotient ring. Okay, so the elements A and B are elements of F2, right? But then, so if I quickly want to make an addition table and a multiplication table for this two, then I guess here I have 0, 1, y, and y plus 1. These are all possibilities, right? And so 1, y, y plus 1. And so if I do 1 by 1, so 1 by 1 is the sum in F2, right? So 1 by 1 is 2 modulo 2, which is 0. So y plus 1 is y plus 1. 1 plus y plus 1 is y. And so this is commutative. And y plus y is 2y, but 2 is 0, so this is 0. And this is also 0. And this is 1, and this is 1. So this is the addition table of this ring. And the multiplication table, so I leave out 0. So simply, I isolate 1 because 1 times everything is that. Y squared. Here I have y squared. I have to make y squared. I have to make x squared modulo this polynomial. And the remainder is, you may say minus 1, but in this field, minus 1 is the same as 1. So y squared is equal to 1. Right? Because the reason is x squared mod x squared plus 1 is 1 in that field, right? And then I make y times y plus 1. This is y squared plus y, but y squared is 1. So this is again y plus 1. And similar here, this is y plus 1. And y plus 1 times y plus 1, this is y squared plus 2y plus 1. So 2y is 0, so it's y squared plus 1. But y squared modulo y squared plus 1 is? So mod x squared plus 1. So when I divide this polynomial by that polynomial, what is the remainder? 0, right? So you see in this multiplicative table, there is the 0. Whenever you have a 0 in the multiplicative table of a ring, that rings the bell that that ring is not a field, right? So this is not a field, right? So if we do the same table with a different polynomial, so for example, we take the polynomial, there are not any polynomials of degree 2, right? Over F2. All right, just I'm running out of time, so okay, suppose we want to take F modulo the polynomial x squared plus y plus 1. Sorry, x squared plus x plus 1. Okay, so again, it looks the same, right? Because the elements are being polynomial expressions of this type, right? A, B are in 2. So again, there are 4 elements. Again, the addition table is going to be identical. The addition is done without using the polynomial I use. Okay, and but the multiplicative table is going to be different. Plus 1. So y squared, what is it equal to? So in order to compute y squared, what I do, I take the polynomial x squared, I do it modulo x squared plus x plus 1, and then I substitute x with y. This is the rule, right? And so when I do x squared modulo x plus 1, remember 1 is equal to minus 1. This is equal to x plus 1, where I replace x with y. So this is y plus 1. Okay, so this is y. Y times y plus 1, this is y squared plus y. When I do the remainder, here I get 1, here I get 1. And y squared plus 2y plus 1, this is y squared plus 1, modulo that polynomial, this is y. Okay? And what you can see here is the nice thing is that this is an inverse. So whenever in the row or the column of an element you find 1, it means that that element has an inverse. So y is an inverse and y plus 1 is an inverse. So the bottom line is that this is a field. Okay, and so we're ready to state our first statement with a little bit of flash maybe. And the statement is going to be the following. So I think my time is almost out, right? Yeah, I have 2 minutes. So this quotient is a field if and only if f irreducible. Okay, and in which case we call it stem field. And the stem is f. F is the stem. Okay? And furthermore, this field contains f, simply the polynomial expression which are, except the first, constitute a set which is the same as f, okay? And actually, whenever you have you have a ring and a subfield, this is not necessarily in this case in which we have declared this to be a field, right? But if you have this, then there is an extra structure that we haven't considered so far. The structure that this is a vector field over this field, right? So the dimension of this quotient ring, which is also a vector space over F. This is called the degree of the stem field. And so I have two exercises to leave you. Very simple. Oh, this is enough. I'm not going to write more than. So exercise 1. So write the additive and multiplicative table of, so I'm going to give you 3 stem fields. The first one is f2 of x over this polynomial, x cubed plus x plus 1. And now when I write this, I implicitly assume here that this is an irreducible polynomial. And so maybe you want also to verify that this is an irreducible polynomial over f2. Okay? So of this polynomial, you'll have to write the summation table and multiplication table, please. And then f3 of x, quotient by the polynomial x squared plus 1. And again, here, I'm assuming that this polynomial is irreducible over f3, which it is, but I guess it needs to be verified as well for honesty. And also, f3 of x. So this is a plus, eh? Otherwise it's minus x minus 1. And again, x squared minus x minus 1, I'm assuming, and please verify it, that it is irreducible. Okay? So this is the first exercise. And the second exercise, sorry, I'm going to use this. Show that the cardinality. So if you take this field Fp, okay, this is a finite field, and then you do the quotient by any polynomial. So the cardinality of this set is p to the power of the degree of this polynomial. Okay, so please show that. That's it. So this exercise 2, maybe I will go back to this. It's nice because it gives us a new way to produce finite fields. You start from this finite field Fp with p elements. If you have at your disposal an irreducible polynomial, then you do the quotient. And if that polynomial is irreducible, you have produced another finite field. And so we'll show that all finite fields are produced this way. Okay? So this is, I think this is to keep you busy tonight is enough. Thank you for your attention, and see you tomorrow.